Okay, excellent. All right, so we are going to try to present two different studies with you today that we've conducted here at Berkeley at the Center for Responsible Decentralized Intelligence, so Berkeley RDI Center. And both of these studies are relating to metaverse privacy. I'm going to start by presenting a study that sort of takes an offensive perspective and looks at attacks in the area of metaverse privacy. And then Gonzalo, my colleague, is going to follow that up with a second study we did looking at a defensive perspective of how we can mitigate some of the problems that we found initially. So we've already introduced ourselves. I'll jump right in after briefly acknowledging NSF, NPSC, Hertz Foundation, and Berkeley RDI, who are all sponsors of this study and provided funding. Okay, so since this is the AI and Metaverse group, we're all familiar here already with the concept of Metaverse, but there are some nebulous definitions as to what Metaverse exactly is, right? The true realization of Metaverse is that everyone is in this one connected environment. We don't necessarily have that yet. So really, to just set the scope of our discussion appropriately, for the sake of this study, we're talking about any kind of multiplayer virtual or augmented reality applications. So we focused on the VR side specifically, but essentially virtual reality applications where you have two or more players interacting within the same environment, we're calling those metaverse applications, even if they're fairly segmented across different apps and so on. And the motivation for these studies was very simple. It was the observation that major metaverse players are currently losing tens of billions of dollars, or 10 billion per year, let's say, in the latest estimates, on selling metaverse hardware at a loss. Right now, assuming that a company with $30 billion of revenue knows how to calculate the bill of materials for a hardware product, right, this has to be a strategic decision that we are going to sell these devices at a loss of 10 billion a year, and we're confident that we're going to make up that revenue somehow, right? And then we want to fill in the gap of what that somehow is in terms of post-sales revenue. But knowing which companies we're dealing with, we might already have some idea as to how they are planning to make that revenue up. But instead of just speculating, right, the purpose of our study is to be thorough about what are the opportunities that companies are looking to exploit in terms of post-sales revenue. And of course, the first thing we think about is data, right? So what kind of data is harvestable from these metaverse applications? Well, there's a variety of points. So to set the landscape of metaverse information correctly, there's a variety of entities that interact with data, right? So the way fundamentally a metaverse application works is your VR device is generating a stream of data, right? A stream of telemetry, 6 degrees of freedom data for your hands, for your head, maybe even audio stream from your voice, all these different points of data that are, by the nature of the application, being instantly streamed to some server and then to other users around the world, right? And this is one of the tricky challenges with looking at data in the metaverse context, is that there is a legitimate purpose for all of your data to be being streamed out of your device, right? So all of that could be seemingly legitimate. We just don't know what is happening with that data once it leaves your device. And so your data goes from your VR device to an application, which is either being rendered on the device itself or on some attached computer, depending on if it's a standalone VR device or not. And then that application in turn is streaming that telemetry data to some server, which is then passing it off to other users, right? So essentially, we have 4 different players, 4 different entities, which are all along this path of data being streamed. You have the device itself, right? And that could be, using your data for nefarious purposes. You have the application, which gets a clear view of your data. You have the server, which is also seeing all your data. And then you even have, and this is the one that's easy to forget, other users who are in the world who are also getting the same stream of data, because their device needs to render a representation of the target user on their screen, and so they're also getting a stream of data about that user in order to render them properly. And so we consider these the 4 different attackers or adversaries who have access to some data and therefore have a potential capability to misuse the data. So when we refer to the attackers 1 through 4, these are the 4 different entities we're looking at. And so what we did in this paper is we set up a study to see just to what extent data is, user data is harvestable within virtual reality. And how does that compare to platforms we're more familiar with, like web applications or mobile applications, where we already have a pretty clear picture of what data is and isn't accessible? And to do so, we set up a fairly simple game in virtual reality. Gaming is one of the most common today applications for virtual reality. And it was an escape room game. So we set up this, designed this game, which was to mimic an escape room. There are various rooms that users go through, completing challenges to try to escape this building. And so we then recruited 30 users to essentially just play this escape room, right? We told them, try to complete this escape room as quickly as possible in virtual reality. But in the background, there were scripts that were observing various attributes about the user, essentially trying to collect as many data points as possible adversarially. But the user just thinks they're playing a game, right? So they're not actually cooperating with any of this data. They're not revealing data unless they are just doing so to complete the game, right? So that's the interesting thing, is this is sort of in the background that their data is being collected while they're going through this game. However, what we did do, and this is fairly unique to virtual reality that you can do this, is we constructed the escape room in a way that was adversarial to reveal, with the goal of revealing as much data as possible. Here's a very simple example of that, right? So in one of the rooms in the escape room, users were asked to move their arms and legs in certain position. They weren't asked to, but it was clear from the room that in order to move forward, you need to move your arms and legs into certain poses, and that's how you unlock something to move to the next room. So users quickly figured out that they need to move their arms and legs. But one of the poses was sticking their arms straight out to the sides, right? And in doing so, we are actually able to capture the user's wingspan. Just look at the distance between their hands, which have tracking controllers on them naturally. And so therefore, the user has now revealed a biometric, which is their wingspan in that case, with probably no idea that they had just revealed information to an attacker, right? They're just following along these various poses, and one of those poses happens to reveal a key biometric. So that's just an example of a way that we sort of carefully constructed the escape room to actually reveal more information about a user than if it was just a totally passive observation, without necessarily still indicating to the user that anything funny was going on. And this is something you can do easily in VR. You can construct rooms or construct environments that prompt users to reveal information without necessarily knowing it, right? And if you were, professional game development studio, let's say, then you could maybe make these blend in even better than we did, right? This is just a research project. You can imagine, big teams being able to really subtly hide data revealing interactions within a seemingly innocuous VR environment. Another couple of examples, right? We had a button that you have to press in one of the rooms as quickly as possible when seeing an object flash. And this was in the background revealing your reaction time, right? Reaction time is interesting. It's not only a unique identifier, but it's a correlate of age, strong correlate of age. So you may be revealing some information about your age just by pressing this button as quickly as possible. On the bottom here, we see another interesting room. I wanted to bring this up to show that environments can be constructed not only to reveal information about the user, but also about their environment and their device, right? This is an interesting set of objects that was constructed without going into too much detail in a way that appears different depending on which VR device you're using. If you're using a very high fidelity VR device, all these balloons appear slightly different in their movement, but a lower fidelity VR device, some of these balloons at the bottom will appear identical. And if you have a challenge where users reveal how the balloons look to them, then they're actually revealing how sort of high-end is their VR device. Okay, and we had various other things where essentially users revealed the their eyesight, how good is their vision. The one on the bottom here is for color blindness. The puzzle at the top, users, we can also see where you're looking at any given time. So users were actually revealing which languages they spoke. You could reuse this to reveal things like product preferences and all kinds of other things. All right, here's a quick view of the experiment setup itself. So we were standing in one area, users were playing here, and then we're being recorded from sort of 360-degree setup. A couple of other things that were happening in the background. This is not something you'd necessarily see in the escape room, but one common aspect of metaverse applications, because you have users all around the world potentially, is that you might have more than one server. You might have multiple servers that you're streaming data to reduce latency. And as a result, you could use the round trip delay time to multiple servers to do like what's called multilateration and actually estimate the location of the user. So if you have more than one server going on, even if you don't have direct access to something like an IP address, which gives location, just the latency to these multiple servers is revealing location. Another thing that wasn't necessarily obvious is that the rooms were set up in a way that users were prompted to explore the corners of their physical environment. For example, to search for things in the virtual room, they would have to go to all sides of the physical room to walk around. And in doing so, because we can track their movement over time, they were revealing highly accurately the size and shape of their physical room, right? Not the virtual room, but where they actually are, to the point where you could fairly accurately guess where they were in their house, right? Or how big their house was, things like that. All right, and in summary, so here's all of the data we collected within just a few minutes. And I want to stress this is not an exhaustive list, right? This is just there's probably a lot more things you can observe, but these were the ones that we focused on. So within just a few minutes of a user playing an escape room game, we were able to learn all of these data points about the user, things like anthropometrics, environmental measurements, technical measurements, etc., behavior, and so on, with a high degree of accuracy, anywhere from 70 to 100% accuracy for all of these attributes. And now, so one thing you may be wondering at this point, so for some of these attributes, oh, why do I care if someone can observe this? Like, let's say height. Why do I care if someone in the metaverse can see my height? Because after all, if I'm walking down the street in the real world, they can also observe my height, right? So this is not anything different. Well, one reason we might care is that these attributes can not only be directly observed, but they can be used to make inferences about your demographics with a high degree of accuracy. So what we did after collecting all this data is we put them all into various machine learning models, which were trained on the participants' ground truth, and essentially were able to observe demographics with a very high degree of accuracy based on these underlying attributes. For example, if we combine height, wingspan, and the voice, we're listening to voice, those things combined provide the user's gender with a high degree of accuracy, right? Similarly, if we look at things like reaction time and maybe vision and so on, then a machine learning model from that can learn your age with a very high degree of accuracy. So it's not just that you have all these attributes that can be observed about you very accurately, but also that an adversary can take all of these things, and because of the sheer breadth of attributes, and I want to emphasize that, even though some of these, like, maybe you can get, let's say you can get fitness. There's one here for fitness. Maybe you can get fitness from a smartwatch, right? Maybe you can get geolocation from a smartphone application. But in VR, you get all of these in one place, right? Whereas previously a company would have to combine maybe 2 or 3 or 4 data sources to approach this level of profile of a user. In VR, it's a few minutes, one-stop shop for an enormous breadth of attributes about a user. And the fact that you have all these attributes in one place and can build models on top of them allows you, is precisely what allows you to make these demographic inferences. So this is also an AI working group. So you're familiar with, of course, the fact that if you have a machine learning model, the more attributes you provide as input and the higher accuracy those attributes have, the more likely you are to get a high accuracy output from your machine learning model. And so again, it's the sheer scope of attributes and accuracy of those attributes in VR that makes this a particular threat as opposed to other types of platforms for inferencing demographics of a user. And okay, so this study has made quite a splash already. We've seen various media outlets picking up that VR is an unprecedented threat for the privacy of users in the metaverse environment. And this is true. We really have not seen something like this before. So instead of ending on that note and taking just a purely sort of pessimistic standpoint on VR, I'm now going to have Gonzalo. Gonzalo is going to talk to you now about another study we did, which was essentially aiming to provide some countermeasures to these privacy risks and give users a tool to reclaim their privacy. Gonzalo, do you want me to keep the slides or do you want to switch to your screen?
No, we can keep your slides and then you kindly could
okay.
change them.
Yeah,
Thanks.
all right.
All right, thank you, Vivek. Appreciate it. So we have seen so far how much data we have extracted from a VR game. And not only that, we also infer many attributes like gender and ethnicity based on this. And this could potentially help companies profile you in a nefarious way and target you for advertisement or other types of political ventures, etc. So we designed also the defenses against this type of potential attacks. And we call it MetaGuard, which stands for Metaverse Guard. And the main tool that we are using that is behind this application is differential privacy. It's a tool that allows you to quantify how much privacy you are leaking into an analysis or when you share data. And this quantification is based on epsilon. So the lower epsilon is, the more privacy you preserve, and vice versa. And basically, differential privacy hampers adversaries to distinguish a data set from another, where in one there is a person and in the other there is not a person. And this indistinguishability gives everybody a plausible deniability. So if we, let's say, protect with differential privacy a group of people that are in a one metaverse session, they will be indistinguishable from the people that are in another metaverse session, even though there might be people that are in both. So that's the main technology that we are using. It's considered the golden standard in academia. And this is one of the first proposals for applications of differential privacy in the real world. Particularly, we're using the Laplace bounded mechanism that for continuous attributes, like your height or your wingspan. And also we are using the randomized response mechanism for binary attributes like your handedness, and it's based on coin flipping. The the good thing about the bounded Laplace mechanism is that allows you to restrict the noise that you add so that you don't become a giant in the metaverse, or you don't have negative height values in the metaverse. And also it is centered around your ground truth, so that it provides this optimal point between privacy and user experience. So your height it's likely not to be too different from your actual height. And basically, in essence, if you want to understand it better, it's just adding noise to different attributes. So with this tool, we created MetaGuard, which we released as a Unity plugin. You can use it in virtually any Unity game, with some exceptions. And once you have it, you can just press a button, and the tool this interface will pop up, and then you can choose different things. The main goal of MetaGuard is to avoid adversaries to track you across different metaverse sessions, so that they can, as nowadays today, companies can track you across different websites. We want to accomplish the same thing by adding noise to the different attributes that you will leak when you are in the metaverse. So we call it the first incognito mode proposal for the metaverse, because there is nothing like this for VR applications, whereas today we see incognito mode in websites and so on. So it's a term that is familiar to the common audience, and this is basically our goal, to start research on incognito mode in the metaverse. Now, this is the interface that was a little bit blurry in the previous slide, and this is fundamental for usability. So these tools should be used by people who don't have expertise in privacy. So if you don't want to bother yourself with which attributes you should protect or not, there is a master toggle. You can turn it on and then you are protected. But if you want to perhaps go in more detail, you can choose to protect only your height or your height and your squat depth, depending on what you want. So also we provide a slider from low privacy to high privacy, so that the user can actually choose how much privacy they want to protect. And why is this important? Is because there are some games that are very aggressive towards privacy. For example, if you are in VRChat, where you are speaking with hundreds of people, you're in the same virtual room with hundreds of people, and they could eavesdrop you, and they can see your movements, and they have your telemetry data, as we saw on the data pipeline in the beginning. Then that's a very hostile environment for privacy. So the user should, if they want, move the slider to the right to highest privacy. Whereas if they are playing on a multiplayer application where they are competing in Beat Saber, which is a game about slicing cubes that come at high speeds at you, and you want to win, then you could choose lower privacy to minimize the amount of noise that your coordinates are going to have, and therefore the user experience is maintained. And this is one of the main things of our research. We want to preserve the user experience of VR, which is one of the main attractions of these type of applications. Now, in order to perform the noise addition, you first need to know where to center the noise distribution. As we said, it will strike a balance between privacy and utility in an optimal way. And for that, you need to center the noise distribution, in this case Laplace, on the ground truth. So there is a moment where, when you turn on MetaGuard will take a snapshot of the different ground truth values, like your height, your wingspan, the distance between your pupils, and so on. So with those values, you will center the noise distributions from which you will sample the noise. And this is necessary to maintain this optimal balance between privacy and utility. Now, how it works in detail is by injecting these offsets into the virtual world. So any virtual reality application, what is leveraging is the OpenXR API that is streaming data directly to the application, to the Unity game engine, and then the game engine will render these virtual objects in the world so that you can interact with them. So what we're doing is we wrote a script to inject new virtual objects in this object hierarchy, so that they are in between the ones that the native ones versus the ones that will be transmitted to the server and to the other users. And these virtual objects that we inject contain this offset, so that when anybody measures these the coordinate, well, checks the coordinates of these objects and measures your height or wingspan, etc., instead of seeing the real or the ground truth, they will see a noisy value, and this noisy value fulfills the property of differential privacy, and therefore it is highly protected with the properties that I mentioned before. So there are some things that you can just change, like for example, your interpopularity distance is hopefully not going to change during your VR playthrough, so you can just make something that we call additive or static offset. So you can just change that and you scale it, right? And otherwise, you have to warp the VR space so that those changes are also reasonable. So if you think about it, VR is a very particular application where if your hands touch on the real world, they should also touch in the virtual world, right? And if you use this technique that I mentioned before of just adding noise to the coordinates, then when you touch your hands in the real world, they might look like this or like this or like that, right? So the user is not experiencing when they should in the virtual world. So we have to preserve the expectation of the user on how virtual objects operate in the virtual world, right? So for that, we introduce dynamic offsets or multiplicative offsets. That means that the noise will scale as the coordinates approach the real measurement. So for example, if your hands are touching, the noise will be 0, but as they keep moving away from each other to potentially leak your wingspan, the measurement in the end will not be your wingspan, but will be the noisy wingspan. So it will go from 0 to your noisy wingspan. And that way we can maintain the user experience and at the same time protect the privacy of the users by only leaking the noisy values of the biometrics or other important values of fingerprinting. So what we did in the end was to run all the experiments that we did in the previous part of the presentation again, but with MetaGuard on. And then we measured how much the accuracy of the predictions went down. So as you can see, I'm not going to go through each of them, but as an example, we can see that height had 100% of accuracy within 7 centimeters, and it went down around 32%, which is a huge decrease in accuracy, even for the low privacy level. As you could see in the slider, you can go from left to right, right? And the more privacy we preserve, the slider was on the right, even it goes higher. But we saw that with even the low privacy level, we had a huge impact on the accuracy, as you can see on this table. Now, one of the most pervasive things that you can do with this data, as Vivek mentioned before, is that you can predict different attributes that MetaGuard is not actually protecting, right? MetaGuard is not protecting your gender or your age, but it's protecting the attributes that will help adversaries figure out which one is your gender or your age or your ethnicity. So if the machine learning model is ingesting noisy data, the predictions will be also noisy. And therefore, we see that gender went down in accuracy by 25%, and even age, which was also at 100% accuracy before, went down almost by 60%. So these decreases of accuracy based on adding noise that is almost imperceptible for the users in the metaverse that use MetaGuard is quite high and strikes this optimal balance between privacy and utility that we mentioned before. Lastly, one of the most important things, one of the main goals of our work was to avoid attackers to track users across the metaverse, right? So if you are in one session, an attacker might collect your data, profile you, and then in any subsequent session, you will do the same with the users. And if those profile match, then that attacker is able to track you. And we call this identification. And before, identification, so figuring out the identity of a person was possible with 100% accuracy. very high. We only needed height and wingspan to identify a person uniquely. But thanks to MetaGuard, now this accuracy went down almost by 95%, which is very close to just 3%, which is identifying 1 out of 30 users that we had in our study. So it's very close to almost random. And this is one of the biggest achievements of MetaGuard, avoid this identification of users. So this was all on our end. I would invite you to check our preprints in archive. Here are the links. Also, we have the implementation of the plugin that you guys can try out in GitHub. And we will very much appreciate if you could share these links with colleagues of yours that might be interested in the topic. So Vivek and I thank you for giving us the opportunity to join you today.
Well, thank you so much, Vivek and Gonzalo. Thank you so much. This was a great presentation. If anybody who is attending has any thoughts, any questions that come to mind, this is the time to ask both Vivek and Gonzalo while they are here. And also see if we want to go to the next level because they indicated earlier on that there is also a demo that you have, which we could be going through as well. But I learned quite a lot with what you just presented actually, and demo may be useful after this too. So we'll decide. But any questions? Anybody? Any comments?
I have a quick question.
Sure.
So the first slide, depicting different kinds of threat, I think is really interesting and valuable. Would it be fair to say that most of the current study focus on the provider side, basically the device and servers and applications? I guess those are the initial target, like how to prevent the provider collecting too much data, being individually identify a person, and also learning about the characteristics of the person. Is that the initial? Have you look at it on the other player side?
Right. So in the initial study, in the what we call the metadata study, and then the other one we call MetaGuard, we look at try to look at all 4 attackers. Now, our attacks actually take place, for the sake of the study, at the application, which we call attacker 2, right? So you have hardware, application, server, and other users. But in our results table, and you are welcome to look at the paper and find this results table, we have this column called attackers, which essentially states which of the attackers are able to perform this attack in our estimation. So we don't replicate all 4 attackers to confirm this, but we have a general idea of what data is available to what attackers. And so, for example, height, we estimate that all 4 attackers, all the way up to even other users, would be able to get your height just by observing your telemetry. By comparison, something like geolocation, we estimate that it would only be available to the application or the server, right? It's hard for other users to have the network level access. So this table here on attackers is our best estimate of which of the 4 sort of data adversaries will be able to perform each of these attacks. You'll notice that a large number of these attacks can be performed even by the sort of least privileged attacker, which is just another end user in the application. So there is, a striking amount of data that is available to even just other users in the metaverse. Hopefully that answers the question.
Yeah, it also, I think so non-privileged means, somebody is just in the game. Yeah.
Yes.
I see. Okay.
So yeah, go ahead. Sorry, Benji.
Yeah, sorry. Maybe a quick follow-up on that is I'm reasonably familiar with the differential privacy methods. So how does that not impact or weaken the ability of the application. You know, up to does that you know, maybe quickly, like what is the application developer have to be aware if the data is coming with that added to it?
Yeah, so Vivek will take it after me because he has more of the developer perspective. But for the epsilon values that we chose and we with which we calculated noise and we injected the noise, we actually did a small empirical study where we chose some epsilon values, we sampled noise, and then we played playthroughs through Beat Saber, for example, the competitive game that I mentioned before. You have to be very quick and take decisions very fast. And we also played other games like Recreational Room, where you play board games and so on. And then we also tried in VRChat. And in those games, we saw how the noise affected us, right? Mm-hmm. And we chose the epsilon values by default so that the user experience will be preserved as much as possible while preserving privacy. So that's how we tailored MetaGuard in the beginning. And we saw that there was a very negligible effect on the user experience. For example, in Beat Saber, like your score, which is ranked between 0 and 100, just changes by a little bit, like a couple of percentage points. If you're very competitive, that might make a difference. But then you could set the privacy level too low. And this is the important thing. We chose for you the default values, but then the user is welcome to choose how much privacy they want to preserve, and from left to right with the slider. So we have the user in mind first, but we have to bootstrap MetaGuard in a way. Vivek, you could complement my answer.
Sure. Yeah, I'll just add a little bit. This is a great question, by the way. So how does it impact a user? As Gonzalo mentioned, this is one of the key focuses of our study. Obviously this incognito mode in the metaverse tool that we developed, not particularly useful unless users actually are inclined to use it, which they won't if it significantly degrades their experience. So the answer is not that it has no impact on user experience, but rather that it has a provably optimal balance of usability impact to privacy. And that's why we bother with these differential privacy tools with this Laplacian noise distribution and randomized response. And this is why we use these sort of intricate mechanisms rather than just putting random noise on all variables, let's say, is that these allow us to provably optimize that for any given amount of noise, right? Specifically for any mean squared error, which is what impacts usability, because a little bit of error, has a disproportionately less impact to a lot of error on the measurement. So for a given mean squared error, you'll get the most privacy value. So that's the reason for this differential privacy mechanism and these sort of mathematical constructs we use, is that there's not no usability impact, but we can guarantee that this gives you the best privacy for the least usability impact. So that's one thing that minimizes usability impact, is just the mathematics of the mechanisms that we use. The second thing is this offset structure, right? So for a given amount of noise, you can sort of naively put the noise on all axes of all measurements, right? You can just throw noise on every variable. Or you can do what we did here, which is we intelligently target the noise at the actual measurements that matter to adversaries. So for example, your sort of vertical axis of your head is much more important than the other two axes of your head, right? Because that is what allows an adversary to observe your height. But the other two axes, if you add noise there, you'll actually get motion sickness when you move your head. So we use this transformation hierarchy to add noise intelligently on the axes and on the measurements that degrade adversaries the most and impact users the least. So those are the sort of two ways that we intelligently construct the coordinate transformations of MetaGuard in order to minimize usability impact while maximizing privacy. And then the last thing, this ground truth, just to emphasize, exists to center the noise around the true measurements of the user. So this ensures that for most users, the observed value will actually be very close to their real value. And again, sort of minimizing the mean squared error. So hopefully that answers the question well, that it's not that there's no impact, but we put a lot of effort into saying that this is pretty much guaranteed to be the most privacy for the least usability impact.
And so this method, I guess, will be most practically used by the app developer. Is that the?
I think this could be inserted in two places. So going back to our, our information flow here.
Yeah.
So I think this. So for our experiments, we inserted this between the application and the server. So between the second and third adversary, we insert this privacy mode, and that's where the data gets anonymized. You could also insert it one step earlier. This incognito mode could be a firmware feature of the hardware, in which case it would be actually stronger. It would protect against the application itself as well. But this would require cooperation of the device manufacturer. So we didn't have firmware level access to these VR devices for the sake of the study. I think that's the ideal implementation, would actually be like before the application to maximize protection within the VR device firmware. But if that's not possible, then you can fairly easily, as an application developer, put this at the application layer and still protect your users from the server and from other users.
Awesome.
Thanks.
So one question that is coming to my mind is, so a usability thing, so great explanation. Thank you so much, Vivek. But what are the possibilities of reverse engineering? Whatever these offsets are being put over here, and these attackers, whether they are inside the game or on the server side, how easy it is for them to reverse engineer whatever has been put in here.
So this is a differential privacy property. There is many good things about differential privacy, but there is one that is key, which is post-processing invulnerability. So if I give you a differentially private height, so your height plus noise, and I give it to an adversary, there is nothing you can do to the noise plus height that can reverse engineer the output. So if you are in the metaverse with all these differentially private values, there is no way for that person to reverse engineer the outputs. Now, we also consider the fact that, imagine you have noise that is just fixed right into your height. So okay, this is plus 10 centimeters. And then the attacker makes an application and prompts the user to lie down. Then the attacker would actually see that there is a 10 centimeters difference when the user should be lying down. So then you would leak the noise. But because we had that in mind, we have the dynamic offset so that when you are lying down, the output telemetry would also be at 0, and therefore we are not going to leak any offsets. And with the post-processing plus the dynamic offsets, we are protected. Now, you could also argue that, as maybe Wenjing knows a little bit about differential privacy, so he might know the privacy budget issue is the more queries you make, then your budget becomes, bigger and bigger, and therefore you might leak some information. The assumption that we make is that because assuming you are using, let's say, a VPN or proxies or Tor to connect to Metaverse, then there's no way they can track your IP, let's say, and therefore they cannot make a connection between your user and the other user that it's you, like the avatars, and therefore there's no link, and this privacy budget is static and it's only for each of the sessions, and there is no connection between them. So those are the three things. So the first one is post-processing Unity. The second thing is the dynamic offset, and the third thing is that assuming you are using other orthogonal protections, the budget will not increase indefinitely.
Yeah,
Okay.
and just to emphasize, the reason that these sessions are unlinkable is because this identity property is degraded from 100% to like less than 5%, and essentially extreme degradation of the ability to identify users using MetaGuard. Therefore, you cannot say link a given user across many different sessions and take a long average and try to get their ground truth, right? You can't link them, therefore you cannot observe more than one session at a time. And that leaves you only with the ability to observe these noisy transformed coordinates, right? And therefore you cannot, because of this post-processing immunity of differential privacy, reverse that through any kind of transformations back to the ground truth of the user.
Great. Awesome. Thank you so much, Vivek and Gonzalo.